Good morning, student. So today, before going into the main topic, I would like to ask you a question. See, suppose here we have two balloons, okay, and the radius of the balloons be R1 and R2. As you can see here, the radius are different. Here R1 is greater than R2. Now, the balloons are actually connected by a narrow pipe. Okay, so I'm drawing the pipe. Okay, this one and this one is to the this is a narrow pipe. What my question is, suppose initially the pipe is in stop. This one is a valve, this one is a valve, and it is in off state. Okay, no air can flow here and there. Fine. Now suppose this valve is taken to on state. Okay, it is open. Now air can flow. So my question is, what is the direction of air flow? Direction of air flow. Let me give you some option. First of all, the air will flow. Suppose this is the first balloon and this is second balloon. So air is flowing from 1 to 2, and the second option is from the smaller one to the larger one, and the third option is no air will flow. No air will flow. Okay, okay. So you think, you take some time and answer. Okay, now I am going into a demonstration video.
If I
Watch it
connect two
carefully.
balloons together, one more inflated, one less inflated, and I open a connection between them, the small balloon actually gets smaller and the big balloon gets bigger. Now,
As you can see that the air flows from the smaller to the larger one. But I know maximum of you answered the 1 to 2. That is, air will flow from the larger to the smaller. But the correct is 2 to 1. Smaller to the larger one. Why? Definitely, there is behind the airflow, the main reason is pressure inside the balloons. So we can explain this demo video, we can explain this phenomena uh, by the topic that we are going to discuss today, that is excess pressure of drop and bubble. Okay, so first of all, we'll discuss the excess pressure of a drop. Okay, excess pressure. What is excess pressure? Excess pressure of a drop, liquid drop. Okay, what is that, sir? Suppose we have a drop, liquid drop. Okay, okay. The atmospheric pressure is P naught and the pressure inside the drop is P. Fine. Now, see, the thing is, suppose we want to increase the volume. Sorry, sorry, we want to increase the volume of this sphere, drop. Okay, how to do that? We have to do some work against the pressure, isn't it? Against the, basically, against the excess pressure. What is the amount of work done? Suppose the change in volume or the change in radius is delta r. This is the new one. Okay, yes, this is the new one. So initially, suppose the radius was r and the change in radius is delta r. Then what is the work done that we have to do? See, it is nothing but force into delta R, isn't it? What is the force? Pressure times cross sectional area, sorry, the surface area, and delta R as it is. But here this pressure is not pressure only, it is excess pressure. Okay. So excess pressure, that is, P minus P naught. P is the pressure inside the drop and P naught is the atmospheric pressure, and the surface area is 4 pi r square times delta R. See, from the concept or the definition of surface tension, we know if the change in surface area is delta A, and if the work that is done to do so is W, then the surface tension is W by delta A. What is delta A? Delta A is the change in surface area, that is final area minus initial, that is 4 pi r plus delta R square, and initial is 4 pi r square. If we take common 4 pi, this r square will be cancelled out. 2r delta R, that is 2ab terms, and the b square term, that is delta R, will be negligible. Delta R square is close to 0. Now if we put these values here, what we are going to get here, it is P minus P naught times 4 pi r square delta R, and in denominator we are having 4 pi 2r delta R. You see, this 4 pi will be cancelled out. We will left with P minus P naught, and 1 R will be cancelled out. Delta R will be cancelled out. So we will left with this only. So from this, we can write P minus P naught, that is the excess pressure, is nothing but 2T by R. This is excess pressure for a drop. What is the excess pressure for a bubble? Before going into that, let us take a message from here. What message we get? See, the message is whenever we are entering into a whenever we are entering into a drop or a spherical surface, there is a change in pressure. There is a change in pressure, that is, 2T by R, where R is the radius, T is the surface tension. We will use this concept. See, this drop is not that thick actually. Here the pen size should be less, this one. Now we'll move on to the excess pressure for a excess pressure for excess pressure of bubble. See, bubble, a usual bubble looks like this, but for the better understanding, let me draw. The liquid is little thick. Why? See, the pressure outside is P naught, and here we have some liquid. Let us take the pressure on the liquid is P1, and inside the bubble it is P. See, when we move from P0 to P1 region, the excess pressure is P1 minus P0 is equals to 2T by R. What is R? Sir, R is the radius of the bubble. Again, when we will move from this point to inside the bubble, the excess pressure is P minus P1, and this is again 2T by R. Now if we add these two equations, what we will get is P1 will cancel out, and we will left with P minus P naught is equals to 4T by R. So this is the excess pressure of a bubble, 4T by R. Okay, okay. Now let us explain the demonstration video. See what we see here. The excess pressure, more the radius, less is the excess pressure. That is, in our question, as here R1 is greater than R2, so definitely the pressure of the first one will be less than the another. That is, here we see the P2 pressure in the smaller one is larger, is more than that of the large surface or the large balloon. So higher pressure is here, so the air will definitely from the smaller one to the larger one, that is from 2 to 1, that is option 2 is correct. Now let us solve an numerical problem which is a previous year's question of JEE. Okay, two spherical bubbles of radii R1 and R2 in vacuum. Vacuum means the pressure is zero there. Combine under isothermal condition. What does it mean? The temperature remains constant. The resulting bubble has a radius equals to. Okay. So basically we have two bubbles, one of radius R1, another of radius R2. They combine isothermally. What will be the radius of the resulting bubble? Okay, so this gives the resulting bubble of radius R. Okay, okay. See, from here we can write the excess pressure, that is pressure inside is P1. Here let's say P2, here P. So P1 minus P naught is equals to, this is bubble, so here it will be 40 by R1. See, here atmospheric pressure is 0. The reason is vacuum. So P1 is equals to 40 by R1. Similarly, P2 is equals to 40 by R2. Similarly, P is equals to 40 by R3. Now they combine isothermally. We know PV is equals to nRT. When the process is isothermal, we can write the N is equals to PV by RT. Okay, N is equals to PV by RT. And for isothermal, they combine isothermally. So N1 plus N2 will be N. N1 is equals to, we can write P1 V1 by RT plus P2 V2 by RT. P2 V2 by RT is equals to PV by RT. Temperature is constant for all of them. Isothermally, it's the combination is going on isothermally, so RT will be cancelled out. P1 V1 P2 V2 PV. Okay, see, P1 is 40 by R, 40 by R1, and V1 is 4/3 by R1 cube, and this one 40 by R2, volume is 4/3 by R2 cube, and this one 40 by R, 4/3 by R3 cube. See, from this we can write that this 40 terms will be cancelled out, this 4/3 pi terms will be cancelled out. We will left with R1 square plus R2 square is equals to, here it is not R3, it is simply R. So this is R square actually, and we need the value R, which is equals to R1 square plus r2 square. So this is our correct answer is option 4. I hope the topic is clear. Thank you.